Hello everyone and welcome to chapter number 6 in the three-phase induction machine course, Starting and Conventional Speed Control Techniques. So this chapter consists of two videos. Video number 1 is dedicated to starting techniques and video number 2 for speed control. I'm not going to explain electric drives here, so electric drives is advanced course. So here I'm going to explain in video number 2 conventional speed control techniques. So let's start. So as I mentioned, the contents of this chapter is starting and conventional speed control, but what are the outcomes? Once I finish this chapter, I will know the necessity of appropriate starting techniques of the three-phase induction motor. So why we need starting? What is the best method for a specific application? Also, we're going to describe the conventional speed control methods and determine their appropriate use based on performance requirements and motor characteristics. So now let us focus in video number 1 about starting techniques of three-phase induction motor. So let me ask you this question. Can a three-phase induction motor be started using a direct online starter? What do you mean by direct online starter? So I'm going to connect the motor terminals to the three-phase block directly or through a switch. The answer is yes. But, and big but here, we need to know why there is some limitation for the starting using direct online. So let us see. Let's refer to chapter number 3 and 5. In chapter number 3, we calculated the rotor current at starting, V phase over root, R stator plus R rotor over 1, slip is 1, square plus X equivalent square. And you can calculate the stator current if you are going to use first approximate equivalent circuit, you are going to add the no load current to the rotor current. If you are going to use second approximate equivalent circuit, stator current will be the rotor current. So in this case, we can simulate that one as we did in chapter number 5. And we had stator current at starting is almost 110 ampere for our example, while the full load current is something like 20 ampere. So the ratio between stator current and full load current is almost 7 times. So I starting equals 7 times the full load current. This means that the machine is subjected to some stress due to the high current at starting. 2 slides back, we asked the question, can the motor be connected using direct online? The answer was yes, but with some limitations. So how we are going to connect it? The motor terminals will be connected to the three-phase supply directly using a switch like this one in our labs or through a contactor and overload relay, either in industry or in our labs as well. Can we use this method for any application? The answer is no. We can use this one only for small motors. What do you mean by small? Small is not clear word. Small means smaller than 5 horsepower. We can accept this method. But that one as well, even if it's smaller than 5 horsepower, we cannot using for this one for critical loads or critical applications. For example, if we have an elevator, so the elevator is a start-stop, start-stop, this means that the motor is subjected to high stresses due to the starting action. Also, direct online gives a high starting torque rather than what is required, and that one results in unnecessary stresses to the motor coupling for the long run. So in conclusion, we need to reduce the starting current by reducing the starting voltage or the voltage. So we need another method or another technique to start this motor. We are going to control the voltage. Let us see. The starting techniques which limits the stator current are controllable supply voltage, start delta switch, adding rotor resistance, and soft starter. We are going to explore each technique to see the features and applications. Controllable supply voltage. In this technique, we are going to increase the voltage gradually from 0 voltage up to the rated value. But bear in mind that the frequency of the voltage is the supply frequency. So if your supply is 50 Hertz, so the frequency will be 50 Hertz from the smaller value of the voltage up to the rated value. 3 techniques can be used here. One of them that adding a resistance, or high power resistance between the motor and the rated supply voltage. So it's high resistance, you are going to reduce the resistance gradually so the voltage applied to the motor will increase. But this method incurs copper loss, so this one can be used for small motors. Instead of using a resistance, we can use auto transformer, and we are going to increase the voltage across the motor terminals using this variac, for example. But we're going to switch this one off when we reach the rated voltage to avoid iron losses. Thanks to power electronics, also power electronics can use controllable supply voltage. We can use back-to-back thyristors or triacs. We are going to control the firing angle. I'm not going to speak about power electronics now. That one is different course. But now power electronics can help us to control the voltage across the motor using the control technique for the firing angle. In this case, you can increase the voltage gradually from 0 volt up to the rated value as well. Let us delve more in the controllable supply voltage technique. Let me remind you about the starting current in case of direct online. We have a high starting current, as you can see here. This means that we need to reduce this value. So what we are going to do, we are going to use, for example, a programmable supply to build that one, which is a ramp voltage increased from 0 voltage up to, for example, 1 second by 50 hertz frequency. So I'm going to use the same example we had in chapter number 5. So in this case, you are going to have the speed is going to increase gradually, as you can see that one, as the supply voltage is increasing from this point to this point for the full voltage. So the speed is going to take this pattern until we reach the steady state speed, which is 1500 RPM for this motor. Then I'm going to load my machine here. So if we look for the current, so the current is going to increase like the envelope, which is opposite to that one. Look for this one and then look for this one. At starting, the current is small and increase gradually to follow the voltage until we reach the steady state speed. So the current reaches the no load current and then we loaded the machine by a certain value. But we have a problem here. We sacrifice the torque, so the starting torque is going to increase gradually as well, so you cannot start the machine loaded. So the torque is going to increase based on the voltage. Torque is proportional to voltage square. So the torque is increased until we reach the maximum point here, until we reach the no load torque, and when we load the machine, we can reach the torque required. So we succeeded to have a starting technique using something like a programmable supply voltage to build a pattern for the voltage we want. Let's look for another example. In our labs, we can use either variac or the supply, which is a variable supply. That one is, for example, a Terco one, and that one is lab volt supply. So in this case, you are going to use the supply voltage or increase the supply voltage manually. So I put here a pattern that we have for 0.5 second 50 volt, another 1 second we have 100 volt, another 1 second we have 200 volt, and so on. So based on that one, you are going to find that the speed is going to increase until we reach the points we want, which is 1500 RPM. I'm not loading the machine here. So the torque, as you can see here as well, that one is going to have a very small value because torque is proportional to the volt square. So until we reach this point, which is enough voltage to achieve a maximum torque, and then we are going to reach a no load torque. At these points, we are going to increase the voltage. So that one, something like d by dt. So that one is going to increase suddenly for the current, which is the voltage applied to the machine. So here we have at 50 volt this current. We increase the current now gradually until this point, while the current for the direct online, if you remember, has an envelope. So here we have something like 20 ampere at starting, while if we have direct online starting, we have something like 100 and 150. Second starting technique is star delta switch, and this technique is employed for the delta connected motors. So the motor should be delta in the running mode. So in this case, we are going to start our motor as a star connection, and then we are going to switch to the delta connection. So why that one? We know from the three-phase system that phase voltage equals line voltage in delta connection. If we start the motor by star connection, so this voltage will be divided by √3 as a phase value. So we have in our motor 3 coils, A, B, C, A, dash, B, B, dash, C, C, dash. If we connect A, dash, B, dash, C, dash together, we have a neutral point. So that one will be star connection, and that one will be used in the starting mode. So then if we connect A dash to B, B dash to C, C dash to A, or we're going to have the opposite direction. So that one will be delta connection running mode. Start to finish, or finish to start, whatever. So that one is delta connection, and we have that one for the running mode. Fine. So in the lab, we can do that one manually. We have a switch like that one or like this one as well. So we are going to connect the motor. Once the speed reaches almost more than 75% of the synchronous speed, we can switch to the from star to delta connection. But in industry or in real applications, something like swimming pool pumps or maybe irrigation pumps, so we can use a star delta. We are not going to do that one manually. We need some contactors and relays and timers as well. Once the speed reaches more than 75% of the synchronous speed, we are going to convert from the starting mode with a star connection to the delta connection or the running mode. So let's look for the wiring diagram here. If we have the lines line 1, line 2, line 3 through overload relay, and then we have a main circuit breaker, so we have the main switch. So the main switch is connected to the motor terminals A, B, C. So if A dash, B dash, C dash will be connected together through this switch, we are going to have a neutral point and the machine will start as a star connection. And after a certain time, we're going to disconnect this one and we're going to connect this one. So if you notice here, A and A dash will be connected through this wire to B, and B dash will be connected to C, and C dash will be connected to A. So you have start to finish, and that one will be delta connection. So let's look for some equations here. In the star connection, star current, phase current equals line current. So in star connection, phase current equals line current equals V phase over root 3 Z starting. S equals 1 in this case. But if you have a delta connection for the same point or the same instant, so the line current in the delta equals root 3 phase current in the delta. So in this case, we have root 3 V phase over Z starting. The ratio between I star line value, which is the phase value at the same time, over I delta line value will be 1 over root 3 multiplied by root 3 will be 1 over 3. This means you reduced the current by 3 times. If you like to write the equation I star phase, which is the same time I star line, over I delta phase, so that one will be 1 over root 3. So if you like to compare between phase currents, you drop the current by root 3 ratio. If you look for line currents, you drop the current by 3 times. Regarding the torque, torque is proportional to V square. So in this case, torque starting at star equals V line over root 3 square over torque starting at delta, which is V square. So you reduce the starting torque by 3 times as well. Let us take an example for star delta switch. We are going to use the same example we had in chapter number 5, video number 1. But I'm going to change the voltage here to convert the motor from star connection to delta connection. So the voltage will be 220 volt. So the same parameters for the same machine, except that the voltage is 220 volt line value for delta connected motor. So when I run that one, I'm going to find that here, this figure shows phase currents. So the dashed line, orange one, if the motor started as a delta, if motor started as a delta. So the starting current phase value will be 101.3. If we're going to start the motor as a star connection, so the current will be 58.5. So use your calculator and check 100.3 over 58.5. You find this value is root 3. So you drop the current by root 3 because that one is phase current. If you multiply that one by root 3, so the ratio between line current to line current, which is the phase in case of the star, will be 3 times. So you drop the current 3 times. Looking for the torque, so if we have delta connected motor, so the starting torque is 57.9, we can say roughly 58 Newton meter. But in this case, you have star connected motor as at starting, so the starting torque dropped to 19.3 Newton meter. The ratio between this one and this one is 1 over 3. So you drop the torque by 3 times. So if you look here, I choose the speed 1330. At this point, I'm going to change from star connection to delta connection. So at this point, the motor is going to jump to follow the characteristics for the delta connection. If you look here as well, so that one is a star connection and that one is delta connection. At this point, the motor is going to follow these characteristics. So if you are going to have any load torque, you are going to follow this region. The third technique is adding rotor resistance. So it's clear that this technique is suitable only for the slip ring induction motors. It's not suitable for the squirrel cage. We are going to add a balanced high power resistance, variable ones. So we are going to add them to the slip rings, and then we are going to cut them in steps to allow the machine to start with high torque and reduced current. If you look for the equations here, I rotor equals V phase over R stator plus R rotor plus R external over S. At starting, S equals 1, and as the machine starts to run, so S will change. So adding external resistance here in the denominator, we're going to reduce the starting current. On the other side, the torque equals 3I rotor square R rotor plus R external. So adding R external here will increase the torque. We might reach the maximum torque at starting. So what the resistance looks like? Something like that one. So that one what you use in the electronics lab. So that one is not suitable for application like that one. So that one is not accepted. Wrong. I'll give you some examples for the real resistance we can use. And we are going to have a conclusion from that one as well. So for example, this resistance is 1 ohm, 1.2 kilowatt, and the size of that one will be 465 multiplied by 69, 119 millimeter. So it's a huge resistance to have 1.2 kilowatt. So this resistance should be a high power because they are going to carry the rotor current. And if you need 1 ohm, you need for this one, this size. I need 3 from those. If we're going to have higher power, for example, the second one here, we have 3 kilowatt ceramic one, but that one is 22 ohms, but we need 3 from these boxes as well. That one will be a huge size as well. So looking for this one, we can increase the power up to 10 kilowatts, but the starting resistance will be 5 ohm. Assume I want 1 ohm with high power, so I need to make series and parallel combination. So for me, that this solution is not feasible solution to reduce the starting current and increasing the starting torque. We can find another solution. Two reasons here. The size of the resistance or the resistance when you are going to make it in a box will be bigger than the machine. And also if there is any fault happen, the machine will going to run in unbalanced mode. So that one is not a recommended solution. Besides the losses we are going to have in this one. Let us take an example about adding rotor resistance. We are going to use the same example we had before in chapter number 5, video number 1. But the machine will be slip ring and we have the voltage 240 volt phase RMS. We are going to add the resistances in steps from 0 up to 500 RPM. We are going to add 1.5 ohm. From 500 RPM to 1000 RPM, we are going to add 1 ohm. From 1000 RPM to 1300 RPM, we're going to add 0.5 ohm. After this speed, the resistances will be short-circuited. So we are going to look for the current and torque. The current will be the left and the torque will be in the right. So if you look here for the current, the blue line shows that we had no resistance. So that one is a normal starting. So with the resistance of the rotor 0.32 ohm, the current is 110.4 ampere. But if we add 1.5 ohm at the starting, so the current drops from 110 to 77.82 ampere. That one is a huge value. So the 1.5 ohm should carry this current. This means that you need a resistance in the range for 10 kilowatts per phase. So we need 3 resistors, 10 kilowatt. Each can carry this current, which is 77.82 ampere. So after 500 RPM, we're going to reduce the resistance from 1.5 to 1 ohm, so the current is reduced. So here we have the change because that one is a change point. So until we reach the current at this point, we are going to change the resistance from 1 ohm to 0.5 ohm. So then we reach this point. After that one, all the resistances will be short-circuited, so are going to follow the original characteristics. Let's go to the torque. For the blue line, that one shows the characteristics without any external resistance. So the starting torque is something like 68.6 Newton meter. If we add 1.5 ohm at the starting, we can push this starting torque up to 190 Newton meter. So I mentioned in the previous slide that this solution I'm not recommended, but some people like to use it for high inertia loads, something like cranes, hoists, some elevators. So you can have a high starting torque. So if the losses is not your concern, so you can use that one to have a high starting torque, as you can see here. You push that one almost 3 times. So the torque, you can keep that one constant if or almost constant for the maximum value, and then you are going to follow the characteristics. If you like to run any low torque here, so that one will be the original characteristics, which is the blue one here coincides with the red one. The fourth starting technique is called soft starter. In the previous methods, we succeeded to reduce the starting current by reducing the supply voltage. But for example, in controllable supply voltage, we sacrifice by the starting torque, and the machine cannot be started loaded. In the start delta switch, the starting torque is reduced by 3 times from delta to star connection. In the adding rotor resistance technique, the starting torque increases, but the resistance itself is a problem because it's a huge in size, and if it becomes faulty, the system becomes unbalanced, and also there are more losses. So we need to compromise between increasing the starting torque and reducing the starting current. Thank you to power electronics, which allows us to have a soft starter where we can control the voltage and frequency during the starting period. So in our lab, we can have a device like that one. That one is a complete drive, but we can use that one as a soft starter. Also, our students can build that one as a final year project. In the industry, you can use a drive like that one, can be used for speed control, and at the same time you can use that one as a soft starter. So it ranges from few kilowatts up to few hundred kilowatts. So how to build a soft starter? Without sophisticated math, I'm going to show you a simple idea here how to build a soft starter. We're going to have the voltage increased gradually from 0 up to rated value, and the rate or the slope from 0 up to capital T. At the same time, the frequency is going to increase from 0 up to rated value. So for a machine 220 volt rated voltage and frequency 50 Hertz, we are going to have the condition that V rated over F rated should equal constant. So for machine 220 volt RMS, so we can say that one as a peak value over 50 Hertz. So that one give you a constant 6.22. So for example, if you have a frequency 20 Hertz, you are going to multiply this 20 Hertz by this constant. You are going to find the voltage here. If you are going for time t here, multiply that one by 50 Hertz is going to give you 220 root 2. So I simulated for you the example we did in chapter number 5. So if you look here, so the voltage is increased gradually from a value here, small value, up to rated value here. So that one is roughly 220 root 2. And here, as you can see, the frequency is going to increase. The waveforms becomes closer, and the frequency increases. And the frequency at this point is 50 Hertz. Definitely, you can control the slope for increasing voltage and frequency. If you look here, I adjusted my program to have the rated voltage and frequency at 0.5 seconds. So you can increase this time or decrease it based on your choice. So what is the implications for increasing voltage and frequency on torque and current? Let us see. Let us apply the voltage waveform to the problem we had in chapter number 5, video number 2. So we are going to have a voltage 240 volt phase RMS, and we have the supply frequency is 50 Hertz, rated value. So V rated over F rated equals 240 root 2 over 50. That one gives you something like 6.78 as a constant. So for example, if you have frequency 10 Hertz, you are going to have a voltage peak value 67.8 and so on. But before looking for the current and torque characteristics, let me remind you about the direct on line from this machine. So we have a high current with high oscillation, as you can see this envelope. So the current here reaches something like 160 ampere. And we have high oscillatory torque response at the starting. Yes, we have a starting torque, but we have high oscillations here. The speed reaches in something like 0.3 second to the steady state value. But when we apply our waveform, the speed reaches steady state, which is the synchronous speed here, in 0.5 seconds, which is the time I adjusted for V over F. So you can see here that the current reduced to 60 ampere from something like 160 ampere. So we dropped the current by 100 ampere. But at the same time, we have something like a torque here. So we have a starting torque. So this method is better than something like controllable supply voltage method. Start delta switch, it depends, and adding rotor resistance. So you can have something like starting torque with reduced current. But you can say that I need a high starting torque with reduced current. So we are going to look for that one in the next chapter. Let us summarize this video. We have different starting techniques for the three-phase induction motor. The first one is direct online starting. This method is simple and low cost, but we have high starting current and more losses at starting. So this method is suitable for small motors smaller than 5 horsepower, but it's not suitable for critical loads even they are smaller than 5 horsepower. So you can use controllable supply voltage technique, which is better control of acceleration and torque. We have a smooth start. But we have a limitation here. That one is suitable for application that require no load torque at starting. Alternatively, you can use a start delta switch, and that one for the running delta mode. So we have simple control, cost-effective method. We succeeded to reduce the current by 3 times, but at the same time, we reduced the torque by 3 times. So that one can be used for medium-sized motors, more than 5 horsepower, up to 50 horsepower or 100 horsepower, and the good application for that one is water pumps. You need a high starting torque, so you can use adding rotor resistance technique. But that one is only suitable for slip ring motors, not suitable for squirrel cage. So you have a high starting torque with controllable starting current, but more losses at the starting. So this technique is suitable for high inertia loads, such as cranes, hoists, or elevators. So the optimum solution is soft starter if the cost is not a limitation. So you have a smooth and gradual start, reduces mechanical stress and power surge. It's ideal for frequent starts and stops. So this method can be used for the most of the applications, such as compressors, fans, and pumps. What will I watch in video number 2? In video number 2, we are going to cover the conventional speed control techniques. See you in the next video.